Today, we're going to read this article posted recently in OpenAI Engineering: How OpenAI Delivers Low Latency Voice at Scale. Voice AI only feels natural if conversation moves at the speed of speech. When network gets in the way, people hear it immediately as awkward pauses, clipped interruptions, or delayed barging. That matters for ChatGPT voice, for developers building with the real time API, for agents working in interactive workflows, and for models that need to process audio while a user is still talking. At OpenAI scale, that translates into three concrete requirements: global reach for more than 900 million weekly active users, fast connection setup so a user can start speaking as soon as a session begins, low and stable media round trip time with low jitter and packet loss so turn taking feels crisp. The team at OpenAI responsible for real time AI interactions recently re architected our WebRTC stack to address three constraints that started to collide at scale. One port per session media termination does not fit OpenAI infrastructure well. Stateful ICE, interactive connectivity establishment, and DDLS, datagram transport layer security sessions, need stable ownership, and global routing has to keep first hop latency low. In this post, we walk through the split relay plus transceiver architecture we built to preserve standard WebRTC behavior for clients while changing how packets are routed inside OpenAI's infrastructure. WebRTC lets us make real-time AI products. WebRTC is an open standard for sending low-latency audio, video, and data between browsers, mobile apps, and servers. It's often associated with peer-to-peer calling because it's also a practical foundation for client-to-server real-time systems because it standardizes the hard parts of interactive media. ICE for connectivity establishment, and NAT, network address translation, traversal, DTLS, and SRTP, secure real-time transport protocol for encrypted transport, codec negotiation for compressing and decoding audio, RTCP real-time transport control protocol for quality control, and client-side features such as echo cancellation and jitter buffering. That standardization matters for AI products. Without WebRTC, every client would need a different answer for how to establish connectivity across NATs, encryption media, negotiate codecs. The coder decoders selected for transmission and decompression, and adapt to changing network conditions. With WebRTC, we can build on a protocol stack that is already implemented across browsers and mobile platforms, focusing our own work on infrastructure that connects real time media to models. We also built on the WebRTC ecosystem itself, including mature open source implementations and standard work that keeps browsers, mobile apps, and servers interoperable. Foundational work by Justin Bertie, one of WebRTC's original architects, and Sean DeBoss, creator and maintainer of Pine, made it possible for teams like ours to build on battle-tested media infrastructure rather than reinvent low-level transport encryption and congestion control behavior. We're fortunate that both Justin and Sean are now colleagues here at OpenAI, helping guide how we bring WebRTC and real time AI closer together. Wow, that's interesting. Two pioneering architects from WebRTC itself are on the OpenAI team. So they must have come together to do something wonderful here. For AI, the most important property is that audio arrives as a continuous stream. A spoken agent can begin transcribing, reasoning, calling tools, or generating speech while the user is still talking instead of waiting for a full upload. That's the difference between a system that feels conversational and one that feels push to talk. That is a primary difference between this and the other audio streaming products. Choosing a media architecture. Once we chose WebRTC, the next question was where to terminate it, where we'd accept and own the WebRTC connection, for example, at the edge, and how to connect those sessions to the inference backend. Termination matters because it determines how we handle real-time session state, media transport, routing, latency, and failure isolation. Option 1. The SFU approach includes AI as a WebRTC participant. Client would interact with SFU, which would then interact with agent, which is connected to inference backend. An SFU, or selective forwarding unit, is a media server that receives one WebRTC stream from each participant and selectively forwards streams to the others. In this model, the SFU terminates a separate WebRTC connection for every participant, and the AI joins as another participant in this session. That can be a good fit for products that are inherently multi-party, such as group calls, classrooms, or collaborative meetings. It keeps audio codecs, RTCP messages, data channels, recordings, and per stream policy in one place. Even in client to AI products, an SFU is often the default starting point because it lets team reuse one proven system for signaling, media routing, recording, observability, and future extensions such as human handoff or adding more participants. Option 2. The transceiver approach terminates WebRTC at the edge and converts to a backend protocol. Client interacts with transceiver, which interacts with inference backend. Our workload is different. Most sessions are one-on-one. One user talking to one model or one application talking to one real-time agent with latency sensitivity on every turn. For that shape of traffic, we choose a transceiver model. A WebRTC edge service terminates the client connection and then converts the media and events into simpler internal protocols for model inference, transcription, speech generation, tool use, and orchestration. In this design, the transceiver is the only service that owns the WebRTC session state, including ICE connectivity checks, the DTLS handshake, SRTP encryption keys, and session lifecycle. Termination here means the transceiver is the endpoint that completes those handshakes and encrypts or decrypts the media. Keeping that state in one place made session ownership easier to reason about, and it let backend services scale like ordinary services instead of acting as WebRTC peers themselves. The core deployment problem. WebRTC needs Kubernetes. After choosing the transceiver model, Our first implementation was a single code service built on Pine that handled both signaling and media termination. It powers ChatGPT Voice, the real-time API's WebRTC endpoint, and a number of research projects. Operationally, the transceiver service does two jobs: signaling, which is SDB negotiation, codec selection, ICE credentials, and session setup. Media, terminating downstream WebRTC connections and maintaining upstream connections to backend services for inference and orchestration. We wanted the service to run like the rest of the infrastructure on Kubernetes, where workloads can scale up and down and move across the host as demand changes. But the conventional one port per session WebRTC model fits that environment poorly because it depends on a large public UDP port ranges that are difficult to expose, secure, preserve as the pods are added, removed, or rescheduled. Port exhaustion. The first problem was the one port per session model itself. At high concurrency, that means exposing and managing very large UDP port ranges. Cloud load balancers and Kubernetes services are not designed around tens of thousands of public UDP ports per service. Each additional range adds operational complexity in the load balancer config, health checking, firewall policy, and rollout safety. Large UDP port ranges are hard to secure because they expand the externally reachable surface area and make network policy harder to audit. They're also poor fit for autoscaling. Pods are constantly added, removed, and rescheduled in Kubernetes. Requiring each pod to reserve and advertise a large, stable port range makes that elasticity brittle. This is why many WebRTC systems move towards a single UDP port per server with application level demultiplexing behind that port. State stickiness. Single port per server designs solve port count, but they introduce a second problem: preserving ownership of each session across a fleet. ICE and DTLS are stateful protocols. The process that created a session needs to keep receiving that session's packet so that it can validate connectivity checks, complete the DTLS handshake, decrypt SRTP, and process later session changes such as ICE restarts. If packets for the same sessions land on a different process, the setup can fail or media can break. That give us a specific target: expose a small fixed UDP surface to the public internet while still routing every packet to the transceiver that owns a corresponding WebRTC session. Comparison of WebRTC media architectures. We evaluated several ways to get there, including turn, traversal using relays around NAT, where an edge relay terminates client allocations and forwards traffic on their behalf. Approach. Unique IP port per session, also known as native direct UDP, pros. Direct client to server media path, no forwarding layer in the data path. Cons. Requires one public UDP port per session, large port ranges are difficult to expose and secure, poor fit for Kubernetes and cloud load balancers. Second approach. Unique IP port per server. Much smaller public UDP footprint than per session exposure. One shared socket per server can demultiplex many sessions. Cons. Works cleanly on a single host, but not across a shared load balancer fleet by itself. Session demultiplexing on a single host only helps after a packet reaches that host. Across a load balancer fleet, the first packet can still land on the wrong instance, so you need to need a deterministic way to steer each session to the process that owns it. Turn relay, protocol terminating. Client only needs to reach the turn relay address port, can centralize the policy at an edge. Cons. Turn allocations add up round trips. Moving or recovering allocations across turn servers is still difficult. Then the last approach is stateless forwarder plus stateful terminator. OpenAI's relay plus transceiver. Small public UDP footprint, transceiver still owns the full WebRTC session. Cons, adds one forwarding hop before media reaches the owning transceiver, requires custom coordination between relay and transceiver. Architecture overview, relay plus transceiver. The architecture we shipped splits packet routing from protocol termination. Signaling still reaches the transceiver for session startup while media enters through the relay first. The relay is a lightweight UDP forwarding layer with a small public footprint, and the transceiver is the stateful WebRTC endpoint behind it. Relay statelessly forwards packets to transceiver. Okay, I'll zoom out a little bit so that we can see the diagram here. Okay, so in the diagram, we have mobile and web, which are both connected to the load balancer. The load balancer is then connected to the relay component that they were talking about, which is directly connected to transceiver, which then talks to inference backends. The relay does not decrypt media, run I-state machines, or participate in codec negotiation. It reads enough packet metadata to choose a destination, then forwards the packet to the transceiver that owns the session. The transceiver still sees a normal WebRTC flow and still owns all protocol state. From the client's perspective, nothing about the WebRTC session changes. Routing on ICE credentials. First packet routing is a key step in this setup. A relay has to route the first packet from the client before any session exists on the packet path itself, rather than pausing on an external lookup service. Every WebRTC session already carries a protocol native routing hook, the ICE username fragment, or UFrag, a short identifier exchanged during session setup and echoed in stun connectivity checks. We generate the server-side UFrag so that it contains just enough routing metadata for the relay to infer the destination cluster and owning transceiver. The sequence diagram shows how the connection is established. Again, we'll zoom out a little. Okay, so they have shown the same components on the sequence diagram too. We have client, followed by load balancer, then relay, and then transceiver. Client sends offer SDP to the load balancer, find random transceiver. This is, I believe, initializing a session, which is why it is sending a request to the transceiver directly. Then the transceiver responds with answer SDP. Then there is a stun binding request to the load balancer, which finds a random relay behind it. It resolves the routing. Stun binding request is sent to the receiver by the relay. Stun binding response is sent by the transceiver. The stun binding response bypassing the load balancer is sent by the relay to the client directly. Then DTLS and RTP come into picture across the layers. And again, DTLS, RTP bypassing the load balancer from the relay to the client directly. During signaling, the transceiver allocates session state and returns a shared relay via WIP and UDP port in the SDP answer. The WIP is a virtual IP address fronting the relay fleet. Combined with the port, it gives the client a single stable destination, such as uh, an example IP, followed by some port. Even though many relay instances sit behind it, the client's first media path packet is usually STUN, session traversal utilities for NAT, binding request, which ICE uses to verify that the packets can reach the advertised address. Relay parses just enough of the first STUN packet to read the server UFRAG, decode the routing hint, and forward the packet to the owning transceiver. Each transceiver listens on a shared UDP socket, meaning one operating system endpoint bound to an internal IP port, not one socket per session. After the relay creates a session from the client source IP port to that transceiver destination, subsequent DTLS, RTP, and RTCP packets flow within the session without re-decoding the UFRAG. The relay session is purposefully minimal, consisting only of an in-memory session to inform the packet forwarding along with necessary counters for monitoring and timers for the session expiration and cleanup. The design choice maintains the packet routing directly on the packet path. If a relay restarts or loses the session, the next STUN packet rebuilds the session from the UFRAG routing hint. To make it even more reliable, a Redis cache is employed to hold the mapping of client IP plus port, transceiver IP plus port, once the route is established so that it can be recovered much earlier before the next STUN packet arrives. Global relay and geosteering signaling. Once we reduce the public UDP service to a small number of stable addresses and ports, we could deploy the same relay pattern globally. Global relay is our fleet of geographically distributed relay ingress endpoints that all implement the same packet forwarding behavior. Broad geographic ingress shortens the first client to OpenAPI hop because a packet can enter our network at a relay closer to the user in both geography and network topology instead of crossing the public internet to a distant region first. In practical terms, this means low latency, less jitter, and fewer avoidable loss bursts before traffic reaches our backbone. The global relay layer receives packets from client and forwards to the transceiver cluster. So this diagram particularly shows where the global relay component they're talking about fits in to the architecture that was described above. So the global relay is placed before the relay load balancer that they were talking about. And so essentially it sits between the clients and the relays. We use Cloudflare Geo and proximity steering for signaling so that initial HTTP or WebSocket request reaches a nearby transceiver cluster. The request context dictates the session's location and which global relay ingress point is advertised to the client. The SDP answer provides the global relay address, while the UFRAG contains sufficient information for global relay to route media to the designated cluster and relay to route to the destination transceiver. Together, geosteering signaling and global relay both set up and media on a nearby entry path while keeping the session anchored to one transceiver. That reduces the round trip time for signaling and for the first ICE connectivity check, while directly shortens how long a user waits before the speech can start. Relay implementation and performance. We wrote the relay service in Go and kept the implementation narrow on purpose. On Linux, the kernel's networking and stack receives UDP packets from the machine's network interface and delivers them to the socket, the operating system endpoint that a process reads after binding an IP port. Relay runs in user space, so a regular Go process reads packet headers from that socket, updates a small amount of flow state, and forwards the packets without terminating WebRTC. We did not need any kernel bypass framework, which would let a user space process poll network queues directly from the highest packet rates, but also add operational complexity. Key design choices. No protocol termination. Relay parses only stun headers and UFRAG. It uses cached state for subsequent DTLS, RTP, and RTCP, keeping packets opaque. Ephemeral state. It maintains a small, short timeout in-memory map of client addresses to transceiver destination for flow state and observability. Horizontal scalability. Multiple relay instances run in parallel behind a load balancer. State is not hard WebRTC state, so restarts cause minimal traffic drops and quick flow recovery. Efficiency measures. SO reuse port is a Linux socket option that allows multiple relay workers on the same machine to bind the same UDP port. The kernel then distributes the incoming packets across those workers, which avoid a single read loop bottleneck. Runtime.logOS thread pins each UDP read and go routine to a specific OS thread. Combined with SO reuse port that tends to keep packets from the same flow, the source and the destination IP port plus protocol on the same CPU core, improving cache locality and reducing context switching. That's interesting. They've done a lot of systems level configurations as well to improve performance. Then the last one they say is pre-allocated buffers and minimal copying keep parsing and allocation overhead low to avoid garbage collection and Go. This implementation handled our global real-time media traffic with a relatively small relay footprint. So we keep the simpler design instead of taking on a kernel bypass route. Results in learnings. This architecture lets us run WebRTC media and Kubernetes without exposing thousands of UDP ports. That matters because a small and fixed UDP surface is easier to secure and load balance, and it lets the infrastructure scale without reserving large public port ranges. With better infra support from Kubernetes and more security due to smaller surface area, this design also preserves standard WebRTC behavior for clients and confirms that an SFU-less design was the right default for our workload. Most of our sessions are point-to-point, latency sensitive, and easier to scale when inference services don't need to behave like WebRTC peers. The broader lesson is that the best place to add complexity is in the thin routing layer, not in every backend service, and not in every custom client behavior. Encoding routing metadata into a protocol native field gave us a deterministic first packet routing, a small public UDP footprint, and enough flexibility to place ingress close to users around the world. A few choices were especially important. Preserve protocol semantics at the edge. Clients still speak standard WebRTC, which keeps browsers and mobile interoperability intact. Keep hard session states at one place. Transceiver owns ICE, TTLS, SRTP, and session lifecycle. Relay only forwards the packets. Route and information already present in setup. ICE UFrag gave us a first packet routing hook without adding a hot path lookup dependency. Optimize for the common case before reaching for kernel bypass. A narrow Go implementation with careful use of SO reuse port, thread pinning, and low allocation parsing was enough for our workload. Real-time voice AI only works when infrastructure makes latency feel invisible. For us, that meant changing the shape of our WebRTC deployment without changing what clients expect from WebRTC itself. And that is all for today.